Hello, Dr. Ripley here with a mini lecture on the Earth, our planet. What makes it a good planet for life? In this video, we'll look at the characteristics of the planet itself and its relationship to the sun that makes life possible on the planet, as well as determining the major climate zones and how the seasons change the amount of sunlight intensity that any given geographic location on the Earth gets as we go around one full orbit of the sun, also known as a year. All right, so for a planet to support life, it needs to have a source of energy, and the sun in our solar system, a star, is going to provide that. It needs to have liquid water, and liquid water, we need to have water um, available on the planet, and it needs to be in the liquid form. So, not all of it in a frozen state, not all of it in a gaseous state or water vapor, but most of it liquid. And for that to be true, it has to have temperatures that, for the most part, and in most areas on the planet, are between 0 degrees C and 100 degrees C. The other thing the planet needs to have is an atmosphere. So that's a layer of gases that is wrapped around the surface of the planet, and it provides molecules that are needed for life processes, and it also protects the surface of the planet from things that might come from space, whether those are asteroids or whether that's damaging UV radiation. All right, so we sometimes call a planet that has these things a Goldilocks planet because in the story of Goldilocks and the Three Bears, she was able to find um, things in the bear's house that were just right for her. So Goldilocks planet is just right for life. So having liquid water that's in this temperature range that allows for life is going to be determined by two factors. So this graph shows these two factors or these two variables, the radius of the orbit relative to the Earth. So this is just another way of saying how far the planet is away from the sun. Right? The radius of the orbit is going to be the distance between the sun and the planet. And this is just scaled so that one Earth orbit is one on here. And these are the other planets in our solar system ranged out across all the distances they are from the sun. All right, so the distance from the sun, and then on the y-axis, we have the mass relative to the sun. All right, so in our solar system, we have the star that we call the sun, and it is this yellow kind of star, and we're going to say it has one sun mass. So there could be other solar systems that have planets that have stars for their suns that are different kinds of stars that are bigger or smaller than the sun, right? So the mass of the sun is going to determine the amount of energy released, the heat and light that's going to get to the surface of the planet. And so if we have a bigger sun, then for it to be the right temperature, not too hot, not too cold, we'll have to have a planet that's further away. And if we have a smaller sun that's not releasing as much energy, then for the temperature to be just right, the planet would need to be closer. All right, so we're going to define a habitable planet as one where the temperatures on the surface of the planet are between 0 degrees C and 100 degrees C, so that there's liquid water and it's common. So notice how this blue-green zone, the habitable zone, goes on a diagonal on this graph. and indicates that the smaller the sun, the closer a planet needs to be to get into that correct temperature zone. And the larger the sun, uh, hotter it's going to be, so the further the planet needs to be away from it. All right. And in our solar system, the Earth is the only planet that's in the habitable zone. All right. So we've talked about why the Earth is a Goldilocks planet, that it's the right distance away from our sun. Now we need to think about why it has an atmosphere, right? So why does this layer of gases stick onto the surface of the Earth instead of floating away or getting stripped away by forces that are coming towards the planet from the atmosphere and from the sun itself? Well, first of all, the gas molecules that are in the atmosphere are able to hover around the surface of the Earth because of the force of gravity. All uh, objects that have mass have gravity. The bigger the object uh, mass, the bigger the gravity. So the Earth is big enough that it is able to prevent the gas molecules that make up the atmosphere from floating off into space. The other thing that could be harmful to the atmosphere that could actually strip it away from the planet, gravity wouldn't be hard enough, pulling hard enough to keep it on, is the solar wind. The solar wind is charged particles that are coming off in a wind from the surface of the sun, and as they blast into the atmosphere, they physically can bump the atmosphere molecules off the area around the planet. All right, so the solar wind could strip the atmosphere away. All right, but so shown in this image is a representation of what prevents that, and that is the planet's electromagnetic force field. All right, so we have this electromagnetic field, and when we use a compass and it points to north, it's using this electromagnetic force field to orient the magnetically charged piece of the compass that is able to be attracted in that direction. And the force field is generated by the liquid core of the planet. It has electrically charged particles in it, and as they flow in that liquid, kind of like lava bubbles up in a lava lamp, as they flow, they generate this electromagnetic force field. All right, and it's strong enough that it is able to protect the atmosphere from the solar wind. All right. So just the mass of our Earth, the fact that it's large, and the fact that it has this liquid core inside the structure of it, not all planets do, is what generates this electromagnetic field that protects us from the solar wind. And both of these things together allow the Earth to have an atmosphere. All right, so when we start looking a little more closely at the Earth and asking why do different places on the Earth have different climates, that's going to relate to the intensity of sunlight that they're receiving from the sun. So just because the Earth is the shape of a sphere, like most planets would be, right, it means that the sunlight that's striking the planet at the equator, so it's going to have perpendicular or 90 degrees to the surface, is going to have the highest intensity. If you imagine the sunlight, the amount of sunlight coming in on these bands of yellow that are shown on this figure, imagine that they're paint, right? And so if we just stroke with this pen and we blop it all onto this distance on the planet, then the density, the color, the intensity of that paint is going to be thick. All right. So lots of energy goes straight to the equator. But because the surface of the Earth is curved and the sun is far enough away that its rays are coming basically in parallel to the planet. If we go up in latitude, right, notice that latitudes are these bands that go across the um, the planet that are parallel to one another, and we've defined 0 latitude as the equator. And then we have degrees going to the north and also going to the south, that are distance from the equator. And when we go all the way up to the poles, we'll have 90 degrees north or a positive 90 latitude. And the South Pole is going to have 90 degrees south, 90 degrees south or negative 90 degrees latitude. All right, so as the latitude gets higher, when that same column or intensity of sunlight hits the earth, it's smeared out across this long distance. All right, so imagine smearing that paint or that pen mark all the way across all these, like way across those many different latitudes, almost 30 degrees of latitude. Right, so the amount of yellow paint is going to be left in any one of those little surface spots is going to be thinner, less intense, less dense than it is. Right, so just the fact that the planet is a sphere is going to cause a decrease in sunlight intensity as we go from the equator toward poles. All right, so when we look at those polar climates or temperate climates, they're not going to be as hot, not going to have as much sunlight for plants to grow, even at the same times of the year. Now, things get more complicated when we look at how the Earth's relationship to the sun changes as it goes around the entire year. Right. So we talk about the seasons of the year. And so we're going to divide the year into different times where, depending on the latitude, you're going to have some different types of climate at these different types of year. And what determines the differences in geographic location of these seasons is not just differences in latitude, but it's difference between if we stuck a stick through a globe or something representing the planet, and we put it through going from the exact North Pole and the exact South Pole. And then we looked at how the Earth is oriented as it goes around its orbit around the sun. We'll see that the axis, the stick that we stuck through the planet, is tipped or tilted. And the angle at which it's tilted is 23.5 degrees. So that exact value isn't super important. But what happens as a result of this is important. All right. So also notice that as the Earth goes around the sun, it's going to have one side that is going to have the sun's rays shining on it, and the other side is going to be in shadow. Now, the Earth is also rotating on its axis, and every rotation as it goes around is one day. All right, so during each of these different seasons, we still have Earth rotating around. And so any point on the globe is going to have some part of that 24-hour period. It's going to be on this side that's toward the sun, and then it's going to be on the side that's away from the sun. So we define those as day and night. All right. So because the angle of this tilt is always sort of on this diagram off to the left, notice that we have um, defined a winter solstice and summer solstice that are the longest extents where the planet is at the the long ends of the ellipse that makes up the orbit. And then we also have the equinoxes, where the planet is at the furthest extent of the shorter axis. And then these pi wedges in between the equinox and the solstice and the equinoxes, we define as the different seasons. All right. So the tilt is going to make different times of the year have different climate. And it isn't really obvious why on this figure. So I want to show you one more figure. And this is an example showing the day, what a day is going to look like at the winter solstice. And this is our Earth, and we've got its axis going from north to south, like I was talking about. And then this green vertical line represents the plane that's perpendicular to the sun. All right, so this is our tilt, the difference between the north-south axis and this green line, right? And notice that the rays of the sun are coming in perpendicular to this green line from the left. So if we draw a line through the center of the Earth, um, and we draw it out into space, then we're going to call that the ecliptic. So this would be the equator if the planet wasn't tilted, right? But the planet is tilted, so the equator is this red line, right? Notice this angle that's labeled little I. Little I is the angle of the tilt. And because of geometry, we see that the angle that we have the tilt from perpendicular to the plane of the ecliptic, or the plane of the orbit, that's going to be the difference between this line that represents this ecliptic and the equator. All right, so now imagine that this representation of the Earth is spinning around on its day and night cycle. All right, so it's spinning, but the sunshine in December is the sun is only going to shine on everything to the left of this green line, and the shadow or the nighttime no light version of the day is going to be on the right hand side of this green line. All right, so if we go up to the Arctic Circle, you'd see that as the Earth is spinning around, at no time during the day is any of the landmass that's north of the Arctic Circle, it's not going to get any daylight at all. All right, so during a period of winter, we're going to have only darkness at above the Arctic Circle. And then as we go towards the equator, we have longer period of the day that these points the at the mid latitudes are going to be in nighttime, and shorter periods that they're going to be in daylight. So we do that explains why we have shorter day lengths during the winter in the northern hemisphere. We have a shorter day length. Planet will these geographic areas won't be as warmed by the sun. They won't have as much sunlight intensity coming into them, and there will be less ability for plants to do photosynthesis during this time of the year. All right, now if we look at the southern hemisphere, notice that because of this tilt, they have the opposite happening. So in December, that's when Antarctica is going to be daylight all day long, 24 hours a day, right? And then we're going to have the summer time period where we have the days that are longer and the nights that are shorter. Right? Notice though at the equator, we basically are going to have the same length day and the same length night, no matter whether we're at either of the solstices or the equinoxes. So one of the things about the tropics, whether near the equator, is that the day lengths are equal during the entire year, and so they don't have a very big, if at all, change in the seasons. All right. So the intensity of how different the seasons are gets bigger as we go towards the poles from the equator. So little seasonal signal is one way that it's said at the equator towards a very large difference between the seasons at the poles. All right, so the combination of latitude and the tilt of the Earth is going to cause these major differences at different latitudes and what happens during different seasons of the year, and those contribute to the climate at those geographic locations. All right, so now you know what's so special about our planet. It's just the right distance from the sun for us to have liquid water. We have sunlight energy to use to power life. Planet's big enough and has an electromagnetic force field around it to protect, to create and protect the atmosphere. And then the relationship with the sun determines the major climates, which in turn will determine what we're learning about in this unit, the biomes.